All right, so we're going to record. All right, so we're recording now. So as you will see at the end, the data encryption standard is actually quite complicated. Feel free to implement it if you want, but it's challenging. So we'll focus first on the on one mode of operation, CBC, basically, just get a feel for how that works. But it leverages off of the XOR code. Okay, so I've got Zoom working here. So now, I'm gonna move to the whiteboard. So to do whiteboards, new whiteboard. Okay, so let's let it load and I'll maximize the screen here. So we're gonna move into full screen mode. Okay. Okay, we got the little thingy there. So use a pen. I'm gonna change the color to red. All right, there we go. All right, so as I said, so things that we're discussing again is XOR, because you know that this is the underlying operation in block ciphers. We are going to kind of focus on block ciphers today. Okay, so block ciphers. Okay, so block ciphers. Modes of operation, right? So we're going to take a look at those, the diagram basically of modes of operations. You've used these already many times when you did OpenSSL. So modes of operations for ECB, CBC, CBC, and so on. So we're just going to focus on a couple of them. Modes of operation. So in a sense, we're kind of like wrapping up a lot of these topics. Okay, and then one of the algorithms we will cover today in more detail is the data encryption standard. And the reason is, I want to show you, okay, there's block ciphers, but then there's something that you've always heard about, DES, right? You know that DES has been broken, and the next step from DES is AES. AES is a much more complex algorithm to implement from scratch. So just let's look at DES, and you'll see that it's in itself quite elaborate, if you will. And so, AES would be just a little bit more difficult. And then it's interesting because once we move to RSA, it's like totally different. Whereas these are just like, let's do a whole bunch of shifts and move things around and jumble the data. RSA is almost like elegant. It's like, wow. How did they do this, right? So I always like that contrast also, right? So we'll look at RSA, and it's got some very, very nice mathematical principles, and then everything evolves from there. Whereas these are more based on, just XORing bits, right? And what the definitions that Claude Shannon gave us for what is a secure cipher. Okay, so that's basically it. So just as a reminder, what are block ciphers? This could be on the exam, right? So there are different ways of breaking up a message, right? We've established, for instance, electronic code books. So I'll just do a reminder of this one. Okay. So ECB, we know that it is insecure, right? It's the electronic code book. That's the example of the squares and the circles, basically. So in ECB, the key is that we take a message, M, right? This is the plain text, so message M, and we're going to break it up into blocks, right? So the blocks are going to be M1, M2, M3, M4, right? So we know this. I'm kind of starting here, and then this is encrypted with some key, right? So you're going to maybe XOR this, and then the result, the cipher, is going to be also some blocks, right? Yeah, so we're going to have blocks like that, where we have sorry, C1, oh, that's M2. C1, C2, just like this is C2. C3, C4. And we assume basically that the key just, repeats, right? So it's the same key for all of these, right? Everyone with me on that one? So what's the problem? If it's the same key, K, 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 K. The problem, as we established, was with ECB, if M1 equals M2, then what can you conclude in ECB? If M1 equals M2, then what's your conclusion in ECB? That C1 is equal to C2, right? Do you guys remember that? Does that make sense, guys? So this is a very important definition, right? So C1, C2. So we have to get rid of this problem somehow, right? And that's why we have these modes of operation. So each block is just, encrypted. And if they're the same, they're going to produce equal ciphers, basically. Okay. So this is insecure. And this is, as I said, the example of the circles and squares. So we need a better technique than that. And so now we're going to look at CBC, okay? And we're going to look at that mode of operation. And that's the one that we're going to implement in the lab this week, okay? So that's the basic idea. And that's generally as far as I'm going to take it as far as coding, because it gets a bit complex, although we are going to look at the algorithm for DES. All right, so now I'm going to go over here. I'm going to add a page. Okay. And so CBC is going to be the model I'm going to look at now. So CBC, right? And this stands for the cipher block chaining. Cipher block chaining. Chain. Okay. All right. So again, the plain text is divided into blocks. Each block is XORed with the previous block to get the ciphertext block, basically. Right. So now we're going to have a chain in there. The message is made unique by introducing an initialization vector in the first plain text box, because we don't have that in the first plain text block. So the best way to understand this algorithm, more so than just looking at it in words, is basically looking at it as a diagram. All right, so we're going to take a look at this diagram and how it would work. So the CBC diagram would be something like this, right? So we're going to have a plain text message. Imagine it's already been broken up into pieces. So I have, and they're going to be all blocks of equal size. We've already solved the padding issues, etc. Right? So we got something like that. Okay. And so this is the plain text. So I'm just going to use P here, P1, P2, whoops, P2, and then P3, right, like that. Now we need to proceed to XOR the values. So here, I'm going to add an XOR operation, but the input to this XOR operation is going to be another vector of equal size to P1, right? And that's going to be our initialization vector, the IV. If you remember, we've been using that, right? And so these IV and the P1, right? So maybe I'll do like that. So this IV and the P1 get XORed together, and they will produce a new block. You should be convinced of that, right? A new encryption or a new XOR block at least. The output of this then, which is another block, I'm not going to draw it here to avoid making this too complicated. But just assume a block, obviously, you should understand, comes out of this XOR operation of equal size. And then over here, I'm going to add a second XOR operation that should take in the key. The key. Do you guys see that? So that's the key. And the key should be of equal size also. I didn't draw it to scale, but it should be the same. And then what comes out of this is what you can refer to as the cipher block. So I'm going to call it C1. Got it? Now, in the next iteration of cipher block chaining, or CBC, we have plain text 2, P2. So that comes in. You know, imagine you're doing this like in a for loop or something. So obviously, it needs to be XORed with something here. And then the result of that comes out, and that's going to be XORed again with the key. So the key is going to be used on every block. And that will produce cipher 2, C2. Do you guys see that? Cipher 2. So the question is, what do you add here? What block goes in here? What do you guys think?
C1.
C1, right? Perfect. Yeah, exactly. And that solves everything, right? And that's why is CBC. And this little trick is what actually made this mode of operation, ECB, when it switches to this, it's secure. And you guys have actually seen this in action, right? So C1 then does that. Got it? So you need, this would, so basically you could say, oh, C1 is XORed with P2, right? And to produce, and then that is XORed with the key, and then you get C2, and then you continue like that. But then the problem with that idea is that you need a block for the first iteration. And that's why the initialization vector basically is created. Remember that the initialization vector does not necessarily need to be the secure key. That's what the key is for, but it's certainly something that needs to be in there for this to run. All right, now let's try the next one. So we've got P3. And P3 then is XORed so this P3 is XORed with something, right? And the result of XOR of that XORing operation is another vector that gets XORed again with the key itself. So as you can see in your, when you implement this in your code, you're going to have basically two XOR operations that are taking place there, right? Unless you can think of a more clever approach. And then, so then we know that from our logic, C2 basically would feed into that position there. And then finally, we get C3. Now, when you guys do the encryption, right, you took the original plain text message. This is what you're going to send, right, in the medium, right, to whoever you're working with. And basically that's going to be encrypted. And if somebody tries to break it to try to find a pattern or do cryptanalytics, they won't. At least we proved this in the very first examples that we did on week 1. Does that make sense? So you guys saw that the square and the circle were gone. You couldn't see them if we were using CBC. Any questions? Does this make sense, guys? So this literally, this one thing you're looking at here is what you'll have to implement for your the lab this week. There are other approaches. I mean, I'll do one more just to kind of illustrate this. It's a very similar idea. It's just moving things around, and some people might give that a different name, but it's a very similar concept. I'm going to create a new page. Okay. So now let's consider something similar to CBC, but it might have different applications. Here we start with an initialization vector. right, of same size. This gets XORed with the key itself now. You can see that there. And then this base, oops, this goes in here. Then that comes out. And here you have another XOR operation where the plain text, so in this case, it would be P1 would come in. Okay. Okay, and then that becomes the cipher. Like that. Okay. And so it's similar. Then in the next step, you would have this would come over here like this, right? And then now you XOR again by this logic, because you don't need an initialization vector. You just take cipher 1, by the way, and you take that, and then by this logic, key would be the next thing here. Key is XORed there, okay? And the output of that gives you the plain text, so P2. Okay, and that goes in here, and then you have C2, basically. So this is just another mode of operation. It's a type of a stream cipher if you want to think of it that way. But now you have this comes out over here, right? You've got the XOR operation. Once again, the key. Just going to write K there. And then the output of this gets XORed with P3. Right? And the output of that would be C3. So it's very similar, just changes a little bit, might have properties of being faster or more efficient in some respects. Any questions? Of the two that we are looking at, as I said, we're going to implement the first one, CBC, and that's difficult enough. Okay. But yeah, so that's the modes of operation. So hopefully that's clear enough, how the blocks basically are organized, etc. Okay. All right. Now that we've defined that, we're going to go back to block ciphers, provide a formal definition of block ciphers. And then with that definition of block ciphers, we're going to drill down into the data encryption standard and just look at that algorithm and how it kind of works. And it should give you at least a nice intuition of how people try to implement these block cipher algorithms in code. Make sense? All right. So let's provide some definitions. So I'm going to start with some general definitions of these algorithms, and then we're going to drill down into DES. So what are block ciphers, right? So this could be an exam type question. I may ask you, what's a block cipher? What are block ciphers, basically? Okay. What is the key idea, basically, of a block cipher, if you think about it? Jumbling blocks, padding, something called DES. Actually, the definition of a block cipher is the idea of mapping n bits to n bits. That's it. That's a block cipher. If you look at it, and I can show you the evidence of it, right? So we went in the previous ones, and this one is maybe clearer. What are we doing? We have these blocks of n bits, and we are mapping them to blocks of n bits. Do you see that? In some scheme. So the scheme doesn't matter. But what matters is that in all the architecture that is created across the internet, etc., what people are doing is they're mapping blocks to blocks. And then you invent your own algorithm in there. And as long as it will do that, it should work as a correct tool, as an appropriate tool. So now let's go ahead and go back to block ciphers, right? So we're going to define block ciphers formally. So what are blocks? The key idea is that it maps, so I'll say key idea here. The key idea is it maps. So it maps the cipher itself, maps n bits to n bits. So I'm going to say n bits. This is important, by the way, because what this is saying, n bits to n bits, is that the block size is the same. Okay, so you keep that in mind. That's a really important concept. All right, so this is your input. And then we're going to map this, right? So I'm just going to say map. Okay, what is mapping usually? It's a function. It's neural networks, AI. What is it? A mapping function. Input to output. Cryptography. Input to output. Pretty much everything input to output. All right, so in this case, n bits inputs to n bits output. N bits of output here. Okay. All right. So then obviously to do this, we need to define this mapping in a more formal way. And that's going to be usually through this mechanism of an encryption and a decryption algorithm, and these algorithms being associated with some kind of a key, right? The secret key. Remember, we haven't yet gotten to public and private key yet. That's RSA. That's like the contrast to this, the beautiful algorithms. These are more like a hammer, but they work. They work very efficiently, right? So let's go ahead and kind of like zoom in on this a little bit more. And we're going to define this one over here. So we're going to say now that we have, this is a more formal definition, a plain text. So plain text. Okay. All right. And this is going to be n bits. N bits. Now this should go through a encryption and decryption set of algorithms. Okay, so this is going to be an encryption and decryption set of algorithms that have in common some kind of a key. Okay, so have in common some kind of a key where the key is of k bits. Okay, and then this gives you ciphertext. Ciphertext. Oops. Ciphertext, which is also of n bits. Okay. Make sense? And these are the algorithms, by the way. Okay, so what are these algorithms? What are they? Well, CBC XOR at the simplest, XOR, right? The one-time pad. What's the problem with that? The length of the key has to be as long as the message, right? But it's secure. So then we need to fix that. ECB is insecure, but CBC, it's a better solution. We just saw why. And then beyond that, DES and AES. We will not cover AES, but we will cover DES today. Just take a look at that one. In more simple. It would take too much time of the semester to look at AES as an algorithm. All right, so that's basically it. Just a few pieces of information. So we've had DES, triple DES, and AES. Triple DES was just performing DES 3 times in a row. Okay, so that was the idea. So now we're going to take a look at the data encryption standard, DES. Right, we've made it to the DES algorithm, which is really should be interesting and fun. Okay, and I'll give you. It's based on some interesting ideas. One of them is something called the Feistel network. So yeah, Feistel network. Pay attention to that one, as there may be a quiz. All right, so pay attention to the logic of it. Right, so should be a fun little exercise to do. All right, so let's take a look at DES, right? So let's go to DES, and this will most definitely be on the exam. All right, so I've said this already, is the data encryption standard, right? So I've already provided a definition of what a block cipher algorithm is. So I'll start there defining DES. So data encryption standard, DES. As I said, data encryption standard. Okay. All right. So we know that it's block ciphers, right? So we already, I'm not going to repeat that is n bits mapped to n bits via E and D. So but that's basically where it comes from. It's a previous graph I did. This was started in the 1970s at IBM. So just some history there. It was broken in the late 90s. DES was broken by exhaustive search, basically, of the keys. And then in the 2000s, basically, AES was adopted as the current algorithm. All of these are subject to being broken if we ever have quantum computers there. But as far as most people know, I guess, publicly, right, they haven't been broken. All right, so let's get started. So the basic idea with DES, right? So DES, what is the basic idea? Basic idea. And think about this as if you were implementing this like in Python in code, right? Think of it in that regard. Just like we did the XOR, that's kind of where you probably want to think. So the basic idea is to build a Feistel network. So the basic idea is to build what is called a Feistel network, probably because of the people who created it. So a Feistel network. Okay. Okay. So a Feistel network uses this architecture called a network, and also uses this set of functions, right? And what do these functions do? They map n bits to n bits, which should be no surprise, right? So that, so we're going to establish some assumptions of what this uses, okay? So we know this is like one. It uses the Feistel network. I'll define that one actually. Then I'm going to define a few more things about DES. The next thing is it uses functions. So given functions F1 ... to F D, basically. It almost doesn't even matter what these functions are because they can be many things, right? But the key thing is that these functions what do? They map n bits to n bits. Okay. So it's not even the blocks themselves, but as it's doing things, it might take a block and split it into 2 blocks. And then one of those blocks will go into a function. And what will that function do? It'll take the original block and map it into another block. Do you see what I'm saying? So it's a lot of like this little trick of like moving things around and XORing operations and just adding like more complexity to the thing. It doesn't, and you will see that this, I like this algorithm, and in contrast to RSA, where it's like this foundational thing of math that, you know, it all makes sense, like very logically, right? RSA will be like that. This is more like, hey, let's just build a network and shuffle things around. That's kind of what I'm implying. Do you see what I'm saying, guys? So that's the idea. All right, so, and they try to add as much like randomness into things and things like that. But these are the assumptions, right? We have the Feistel network, which we need to define. That's the basic idea. Given functions f1 to fd, these functions map n bits to n bits. I'll even say in some scheme, that it almost doesn't matter. In some scheme. Whoops. As usually these are variable things, etc., of the algorithm. Do you have a question? All right. So now, you know, we've defined these basically, these f1, fd basically, because they are n bits to n bits, we can say that they map a set of zeros and ones of size n to another set of zeros and ones and of the same size, right? So size n basically. All right, so now let's define the Feistel network and take a look at how it works, okay? So this should be the next idea, right? So maybe the pop quiz will be based on this one. So let's take a look. So the Feistel network, what is it, okay? We have a block. Now imagine it's just, we had the message, we broke it up into blocks. Maybe it's of size 64. And we're going to split it into 2 blocks of size 32. You see where that's going? So that's kind of how it works. So then we're going to say, whatever it doesn't matter, we just say n bits, n bits. Okay. And then basically these blocks need to go through a network, almost like it's sliding through that network. There's going to be XOR operations, etc., until you get at the end, no surprise, n bits by n bits, right? So in this case, then, let's consider the block. This is, you know, the whole block. It's going to be split into 2. So now I'm going to relabel them basically. As R0, which will be right 0. And then left 0, L0. And they should be of equal size here. Okay. All right. So I have my blocks. And now what do? These blocks are going to be transformed into another set of blocks of equal size, but in some scheme, using these f functions and also just XOR operations. So R0 basically just slides and becomes L1. Do you see what I'm saying? It literally just becomes that. Okay, that's the logic of the Feistel network. This is how the Data Encryption Standard, you know, was defined initially, right? So then we have L0. So how does L0 work? To create this one, right? So now we're going to create that one. So we're going to have an XOR operation here. So we got XOR. L0 goes into this XOR operation. And what comes out of that becomes R1. Do you see that? But something else needs to happen here according to the definition. R0 goes into this function that we define F1. And that function takes the block R0 of n bits, and guess what? It produces a block of n bits in some scheme.
What was that last thing you just said?
What
was that last thing you just said?
R0 goes into the function F1, and what comes out of that is another block of size n bits. So this is n bits, this is n bits. So that's what we defined previously. So do this one. These F functions map n bits to n bits in some scheme. So that's the Feistel network, where inside there's going to be a whole bunch of other XORs and shiftings and things like that.
Yeah.
But at the overall level, that's what it's doing. So I'm going to go over here. All right. So R0 then goes into F1, and F1 produces a vector, and that vector gets XORed with L0 to produce R1. Does that make sense? Is my scale, my drawing not to your liking? Should I redo this? Do you understand the I know this came a little crooked here.
Where does L0 come into place then? If R0...
L0, so I'll do this again. All right, so here, this is just the same thing that I renamed it as R0 and L0. Okay, just so that there's some logic here. All right, so we said that R0 just slides down. No transformation whatsoever. So literally R0 is just L1. But to get R1 here, we take R0, this block here, run it through this function F1. What does that function do? It takes a block of n bits and produces a block of n bits. Okay, so it did some operation that we're not even going to define. So then it comes out here because it can be many things. L0, this other block, which is also n bits, goes in here. These two get XORed, and the product of that, I'm trying to goes like that into R. It becomes R1. Does that make sense, guys? This is in the forward pass, by the way. Forward pass. Okay, I'm going in that direction. So that implies what? Encryption. But remember that DES also decrypts. So what does decrypt mean? Going backwards. And this works, right? So let's do a few more examples. So now we've got R1 and L1, right? So these are going to be, now this Feistel network can be as long as you want it to be, as long as your computational power will allow, because the longer you make it, the more operations you have in there. Do you see that? So you're incrementing the performance or affecting performance, let's say. Excuse me. So now R1 slides, right, following the same logic, and becomes L2. Do you agree? And this should be R2 and should follow the same previous logic. So that means that R1 should go into F2, another function that you have defined, right? Sorry, it's a little tight there. Okay. You guys see that? Let me redo this one. This one just slides. Okay. And this should be F2. So I'll just draw it like an F like that. F2. And it's a function, right? That function takes in R1 and produces a vector of the same size. L1 then comes out here. These two get XORed, and the result of XORing these becomes R2. Making sense? That's literally DES. This algorithm is just a bunch of XOR operations. There's nothing else going on here. Okay? Then I can continue. So I'm in R2, L2. I'm just going to do the final layer because this can be as long as you want it to be. So dot, dot, dot. Right? So I'm going to do the last one. Oops. Let's do the last one. Okay, so we're going to have, let's say, RD minus 1. RD minus 1. And then this would need to be LD minus 1, right? LD minus 1. Okay? And so now we want to calculate I'll make this a little bit bigger. We want to calculate RD and we want to calculate LD. Right? So that's, we're following the same logic kind of algorithmically, right? And so what's the process? RD1 is literally LD, correct? By the same logic. And we finish the encryption. And notice this is, at least for this block, is fully encrypted. It's n bits by n bits. Over here, we have n bits by n bits. Got it? Questions so far? All right. Now, the other part would be RD minus 1 will go into a function, which in this case will be function D. Right? What does this function? It maps n bits to n bits. So that produces a vector. That vector is XORed with LD minus 1, which is over here. And that basically becomes RD. That's it, right? So you guys hopefully can see that. So therefore, if you were doing like an algorithm, oops, here, therefore, what would you conclude? You would say, for this example, Li, that's the easy one, is always Ri minus 1. LD is going to be always RD minus 1. Or if this is Ri, then Ri minus 1. Do you agree with that? So Li, like if it's L0, if it's L1, then it's R0. If it's L2, is R1. And you can see that here. Do you all see that? Okay. And so what about the other one? Ri, for this example, it's a little bit more challenging, right? Ri would be what? Ri is this one, right? RD. So that's going to need to be, so for Ri, it's going to be Fi, right? So the function, notice the index matches Fi, which takes in as input Ri minus 1. Right? XORed, remember, this is not a plus, but an XOR operation with this one over here, which is Li minus 1. And that should generalize for all. Do you agree? Try it just at a step, L2, or we're predicting R2, right? So if we're predicting R2, then it's F2, okay, F2. It takes in R1 as input because it's I minus 1, and then we XOR it with L2 minus 1, which is L1. Got it, guys? Pretty easy, right? You can totally implement this in code. Okay. Now, just as an exercise to test your cryptographic abilities, take out a sheet of paper, right? And I will give you a similar problem, and just give you some time to try to solve it, okay? So basically, I'll give you some background here, right? So what did I do here? I'm going forward, right? If I'm going forward, what does that mean? It means that this is the encryption, right? So the question now will be, I'm going to write it in a different color so that you understand that this is the question. Okay. Do the inverse or the decryption. So now that way. Okay. So the inverse. And I'll give you something so that you can think about it. So given the previous logic, how would you invert the process? So you did encryption. This would be the decryption part if you want to think of it that way. So quite simply, for this diagram that I'm going to draw here, okay, so I'm going to say R I, and this is going to be Li, right? And here I'm going to have the next one, which is going to be Ri plus 1, right? I plus 1. And this one would be Li plus 1 with the same logic as before, but in reverse. So we know that it goes like this, right? It goes like that. Then this one comes in here, and notice I'm going to use the notation Fi plus 1, but this should be consistent with what I did before. I'm going to do a circle there. That came out good, actually. And then what do? I XOR it, right? With Li. And the result should become, all right. So now what I want you to do is give me, because we're going in reverse, that way, you're going to have this, and I need to find this, not how we were doing it before, where I had this and I got this, right? So I need you to define these formulas, but in this diagram here, for Ri and for Li, and that's it. So I'm going to add a question mark. That's it. Do you guys understand? Yeah. So I went over the logic, and I'm trying to keep everything in one slide. So it's like, you have it. You have all the information there, right? So the example I did is the forward pass, which is the encryption. But DES also decrypts, right? So you're going to have to reverse the Feistel network, right? So that's all I'm asking is, instead of giving me, when I wrote these equations here, it was basically give me RD given RD minus 1 and LD minus 1, for instance, right? But now I'm asking you to give me RI and LI given these, because we're going in reverse. So that's why I wrote RI and LI. What would they be? You just have to reverse the logic. And it's the same logic as before. It hasn't changed. Just go back. So you have this, right? So you have these two. Give me these two. By using the same logic, but just write out these equations over here in reverse. One of them is pretty easy. One maybe not so easy. So think about it for a little bit, and then that's what's basically what you would have to do with that. So you can see it's not straightforward. And take your time. Better? Imagine it like a physical, like a thing, like a railroad, right? How would these cars go through this railroad back and forth? This is similar to a problem we did at the beginning of the semester. There's similar, just much more complicated, but it's a similar idea. Do you have a question? You can ask questions. Just
Okay.
don't give the answer.
So you're saying we need to reverse the process.
Right. In that, yeah. So we went, here's the red arrow. We went in that. So we started with these blocks. So we always had these and we predicted the next two. We had these and predicted the next two. So these equations are written in terms of that.
I don't know if I'm missing
But
something.
now it may be so easy that you already have a solution. Now you would have these, right? The ciphers, and they're just becoming less of a cipher until they become plain text initially, you know. So you're reversing in that direction. Assume you have this and this, get this and this, but give it to, you know, answer it as an equation like I did over here. As if you were implementing this logic in code, for instance. I mean, you know what XOR does, right? So XOR has some properties that we already established, right, in the previous quiz. So this one, yeah, XOR reverses. Yeah, exactly. So message, key, cipher, message, key, and so on, right?
Wow.
But that's fine. But just make sure you get this right, because this is not just XOR operations. There's some logic of the Feistel network itself. Okay. But yeah, you know this, right? So you need to tell me though, like this LI is equal to in terms of that, and this Ri is in terms of that because this is what you will have. Right, so just reverse it. We'll think about it for a second. One is super easy. One of the two equations is super easy. One of my points is there is a pattern in this one, which is not what you would want in an algorithm, but it's much more complex to find, right? So the other one's just to torture you guys. That's a good question. So you're stuck there, right? The function is not reversible. That's a good question. Yeah. That's a good question. Function is not reversible. So you can only use it in one direction. But we defined it as mapping n bits to n bits. So you know that. Actually, the solution to your question is the reason why the network is the way that it is. Because it allows, otherwise it wouldn't work. Just think about it. There's like a little trick in there. And then once you finish your quiz, just put your name on it for sure, and then bring it up here.
Guess I'm gonna pause.